Hello, my name is Patrick Webb, and we're considering the chemistry of plaster in heritage building, and we're at the point we're going to consider the natural cement cycle in part 12. So, as previously discussed, natural cement is a clay marl composed of limestone, calcium carbonate, silicon dioxide, the active version, and alumina. In the manufacturing process, we add quite a bit of heat. Looking at 1200 degrees Celsius, somewhere around as high as 2200 degrees Fahrenheit. Again, freeze up the lime to be able to react with the aluminas and the silicas, because the CO2 is dissipated. So some of the compounds that we're left with is dicalcium silicate, just like we had with the natural hydraulic limes. And then we're starting to get some of these alumina compounds. We have the tricalcium alumina, and then the tetracalcium alumina ferrite. And there's actually several more in lesser quantities, but those are usually the two principal ones that govern the reaction. And sometimes there's a measure of quicklime left that's not been consumed by the silica and alumina reactions. At this point, generally speaking, there's no need, because there's such a small quantity of quicklime, there's really no need to quench it. So sometimes a step happens in the manufacturing process, sometimes it doesn't. It just depends on how much quicklime is there. So really, we're just going to go straight to adding water for use as our plaster. So that's what's going in, H2O, on the job site. And we're going to get 3 different reactions. And I'm going to present them in the order that they take place. So first, we have our free lime that is combining with our aluminate clinkers. And that's going to create these calcium aluminates, hydrous calcium aluminates. And that's where we get our really rapid set from. Those compounds can set anywhere from 5 to 15 minutes. A lot of times we have to even retard the natural cement to be able to use them depending on the application. But that's just an initial hardness, an initial take. We're still going to benefit from all those hydrous calcium silicate compounds that are forming. And that's why it works great with natural hydraulic lime, because basically they're the same, have the same type of chemistry, just in different ratios. So they'll have the same bell curves, for example, over time as they're curing out. And then, if we have some of this quicklime left, usually we have some, we're going to get, over time, some calcium carbonates, as well as some of that valuable free lime in the system. That way, if there's some cracking down the road, there'll be some opportunity for some healing as well. And that's going to reabsorb a little bit of the CO2 that was lost in the manufacturing process. So I did want to speak about that, kind of give you the breakdown about how much CO2 is lost in the manufacturing process. We'll start with lime. And generally speaking, you're able to recapture about 90% with lime, or more. Maybe we'll put a 90% plus. With the natural hydraulic limes, just depending on how hydraulic they are. You've got a range, so probably somewhere between 60 to 70% of the CO2 gets recaptured. And then with your natural cements, well, if they're going to be used like underwater, for example, there's not going to be opportunity to recapture CO2. But in most situations above ground, maybe you're somewhere in the neighborhood of 20 to 40%. Very good. So now we've considered all the heritage binders, really. So it's going to be interesting to see how and which ones play nice together.